guys are funny. Like, we don't do YouTube, Jeff. Maybe you did Vimeo. We do that. Vine or. I'm throwing these words out. I have no idea.
Snapchat.
Yeah. Whatever the hell that is. Twitter now is like old.
Yeah, it's not that cool anymore. I only go on it.
Just now setting up my MySpace account. Is that? MySpace sounds interesting.
Even Tom got
I know. Yeah. Tom has defriended you. Tom has defriended everybody.
Do you have a Facebook Instagram?
I do.
Ah, so you kind
I sort of want to delete it, but
of, you just can't get yourself to do it. I'm in the same boat as you.
I'm on there like once a month, basically. So.
That's what they all say.
I mean, and the weirdest, I mean, you get the weirdest updates, people, but and I'm like, the people I really want to keep up with, I think I'm keeping up with.
Right.
You know? The weirdest requests, students will find me. Mr. Waller, hey, will you add me? No, I won't yet. Sorry.
You don't take this personally, but what section? This is 310.
310, yeah. Yeah, so f of a, which is f of 0, is what? 1. F prime of x, if you write this as this, it would be so those cancel. F prime of 0 would be 1 over 1 plus 0 to the 2/3. That's 1. Is that cool? So now you got everything you need. Right? So it's really nice when you use a equals 0. So you get cube root of 1 plus 3x is approximately 1 plus 1x minus 0. So that's insane if you stop and think about it. Near 0, this function can be approximated with add 1 to the thing you're trying to plug in there. Right? Now, the next step is the part I was telling you about before. You got to be careful, figure out what the hell x is to get the actual value they are asking about. So if you look at the next part, of part A actually, we're not on part B yet. State the corresponding linear approximate and use it to give an approximate value for cube root of 1.03. What would x have to actually be to make that 1.03?
0.03.
Yeah. So here's what you can do. You can just say I want that to be 1.03. So I want 3x to be 0.03. So I want x to be 0.01. Right? Because you got 3 times the thing in there built in, yeah.
Would you get that 1? You just plugged in 0 to the...
0 to the function.
And that...
One piece of my linear approximation needs f at a. A is 0, so f at a is cube root of 1 is 1. Let it be easy. So I really just need 2 things. I need what's the function value at the point you're expanding around, and what's the derivative's value at the point you're expanding around. That's all you need. Let this be easy. Yes, sir?
That equation right there, f of x equals about whatever.
Yeah.
F of a plus f prime a. What is that?
So that's y equals y1 plus m times x minus x1. That's what that is. Right? Fa is the specific y1. Fx is my general y. X is X, X1 is the specific A, and M is the slope at A. Right?
So for f prime a, you got 1.
Yeah, F prime of X, we did it here.
How did the 1/3 cancel out again? Sorry, I wasn't paying
Chain rule 3.
Oh,
Yeah. That's the hardest thing to remember, especially if it's at the end of a long ass thing of stuff you've already done. You almost always forget to do the stupid little constant. The coefficient comes out as a chain rule. Yeah. All right. So now we know to do this, it's going to be approximately 1 plus my x is 0.01, so it's 1.01 approximately. What is the cube root of 1.03?
1.0099.
So the actual value, cube root of 1.03 equals 1.0099, whatever. That's good, right?
How did you just get rid of the square root, the cube root over the 103 to then set up your cube?
That's the beautiful thing. These are values. Those are values. I plug stuff into my function and my derivative. So to get f prime of a, I plug 0 in.
I've got all that. But now when they ask you to use that with the 103,
So now I know if they ask me to anything that I can put in this form where x is close to 0, I can use this instead.
okay,
So to get 1.03, x had to be 0.01 to make it 1.03, right? That was this work here. What does x have to be to get the value that I want?
So you add 1 plus 0.01 right there.
So to do it, you can always just say, I want to force this thing to be this. And that's what algebra is for, right? Force an expression to be some value. You can figure out what x has to be to make that happen. Most of the time, you should be able to just figure it out. You should know it's 0.01 to make 1.03 at the end. So now, because the biggest mistake I always see is people, either they put 1.03 there, or they put 0.03 there. All wrong. X has to be 0.01. And you can always check it against, if it's not very far away from the thing you used, it should be really damn close to what it's supposed to be. So if you get 1.03 there, and it's supposed to be 1.009, you did something wrong. Right? So it shouldn't be that far away. If I've only, and I got to be careful because it's not always true. Because like we said earlier, some functions are insane, but a cube root function is nice. It's an interval of working. What's a good name for that? Should be relatively large because it's a nice, smooth function, right? It's not something going crazy. Okay. All right.
So when you finish the graph and it's asking for what points you do you set a domain type or a domain type thing?
So let's do this one because this is actually part B of this problem. And again, it's always freaking 0.1. Determine the values of x for which a linear approximation is accurate to within 0.1. So if we put it in here. So again, can we just jump to the thing? Now I want in the middle I want my approximation. 1 plus x. On the ends, I'm going to want let's see if we can get this in there. Oh, what was the function? Cube root of 1 plus 3x. Minus 0.1. And I think there is a cube root button there. Yeah. Cube root of 1 plus 3x. Under math, yeah. Plus 0.1. You guys with me? Can we
because you wanted to go from 0.1 up and down?
Yeah, I want to be within 0.1. I want my...
Is that like the epsilon delta stuff?
Again, it's sort of like that. It has the same feel to it, but not really.
You find where the 2 points, and then you write down.
So I want my y2, I want my approximation to be within those two things. No lower than 0.1 of the output, the real output, no higher than 0.1 of the real output. So when I graph this, I can kind of see which one of those is really going to be what oh god. And of course my zoom sucks right now because it was for the other function. Stop thinking. Stop it. Okay. Go to zoom 6, just start off now. Now here's at 0. Okay. Here's my approximation, so it looks pretty good. So now I can see I want to zoom in like right here. Zoom in like that. Let's see if I caught everything. Alright, here's my floor. Here's my approximation. And here's my ceiling. You can see it hits the ceiling there and it hits the ceiling there. So I could take my, let's take Dan's suggestion, get rid of my floor.
Will there ever be a time when it's both?
I never want to say no, but the thing is, tangent lines will almost, they have to hit it just once right there, right? But it actually does depend on how crazy the function is. I can't remember, I think the book has, I don't think they have an example where it hits both. Most of the time it's just going to hit one or the other one. Because it's going to, the function is almost always going to curve away from it. So it would be the roof or the floor that's going to hit it. So now you just find those two intersections like we did before. Is that cool?
That's what I was saying.
But for your answer, like how would you write that? Would you write it as
An interval, yeah. Yeah. So whatever this is, comma, whatever that is, inside parentheses, yeah.
I have a question.
Yeah.
When you have a product rule and a quotient rule, which one do you do first? Like, let's say you have a product rule on the top.
So if you had something like, this is probably exactly what you're thinking about, right?
Yeah.
I know, I was in your head. So, the overriding thing here is, what? What do you think? And actually, there's a lot of different ways to look at this. Could I pull this out front? Make it look like a product between an e to the x squared and some quotient, so then it depends on the way that you think of it and how you write it. I would think of this as the quotient of that function and this function. So within the quotient rule, I would have product rules. Right? So you almost always have an overriding rule, and then within the little parts of that rule that needs a derivative, you have other rules that apply. Does that make sense? That's what I've tried to say. I think I just said it the best I've ever said it.
I'll see when we do.
So the rule, the quotient rule would say, what?
F prime G.
Good. So that F prime means the top prime, right? Times the bottom. Minus.
The bottom prime.
Good. Good. All over the bottom square. So now use. Oops, God. Square. So now within here there's a product rule. Within here there's a chain rule. Right?
But first you do the quotient.
Yes.
And then.
And this is what I meant by always saying, write the rule, don't do the derivatives first. Because then you can lose something very easily. Because in the middle, if you're doing the derivative and you're in the middle of writing a rule, you're going to miss something out of that rule, possibly. Does that make sense?
Yeah.
So if you just focus on the rule first and then worry about the derivatives, you're not going to lose something that the rule needs.
You wouldn't be wrong if you did it either way you wanted, though.
You wouldn't be wrong. But I'm trying to keep you from where people always make mistakes. Yeah, and it's always the way that you have to have too much going on in your head at once, right?
Would you bother trying to turn that bottom one into a -1 to bring it up on the top so you could?
Yeah, you could do that. You could do natural log cosine to the -1. Bring it up top and then just make it a triple product rule, right? Nothing wrong with that. Yeah, I like that one, don't you? I'm gonna try. I gotta give you one problem where there's quite a bit going on. Just to make sure you can track it. As part of the skill you're supposed to develop here is, can you track what a rule needs and can you not lose anything? But obviously I'm not gonna give you 8 of them that have like, massive amounts of junk that you have to keep track of.
So that like perfect must have to break down while the other one is walking in the other room.
Oh,
Wasn't that what you said about?
with the oral final exam,
You have one problem.
we had one problem at a time.
Oh, at a time.
We had like 4 problems.
Oh, okay.
So he'd give us a problem, and then he'd come back to all of us, and a girl sitting next to me in the next room had a nervous breakdown. Seriously, she had to be taken to a hospital. While we were doing our oral final examination for quantum mechanics, the teacher come in and say, here's the problem, this thing is here, and this is there, and I'll be back in about 5 minutes to tell me the answer, and we're like, shit. And then, of course, the girl next to me is just, and I'm like, that was a good memory. Cool teacher, though. All right, so anything else from practice test? Or,
Test
yeah.
on 1G, how did you get from 8 to 4?
1G. Oh, I took a 4 out. Where'd my 2 go then? That's a good question. Yeah, let's do that one again. As you can tell, I kept changing my numbers. All right. Yeah, it should be twice. Oh, I did have twice, and then I changed it back. Okay. Anyway.
What problem?
This is 1G. What is it? 4x plus 7 squared. Right? 5x cubed. To the 4th. Now, there's nothing saying you can't multiply that all out. Except common sense. And normally, what you'd want to do at the end of this problem is a very classic question would be, where does this thing where does it go flat? Where does it turn? So that's why you almost always want to take this in the direction of factoring, which is why you'd almost never multiply this thing out at the beginning.
When does it turn or go flat? Oh, I understood that.
All right, let's find out.
Velocity of 0?
Which would mean what? Set what equal to 0? Slope, exactly, which is in calculus the derivative, right? So that's a very classic problem. You find f prime, and then you see where it turns, which means set f prime equal to 0. So to find f prime, let's really break down what I was trying to do all at once. Derivative of this, it'll be 2 times 4x plus 7 to the first times 4. That's the chain rule piece, right? So that's the 8. And leave this guy alone. Plus, leave the first guy alone. 3, 4.
Sorry. Something there.
Third.
5x squared. 15x squared.
Oops, is that it?
6.
Thank you. Alright, so now here's the 8. I think what I did was I left something out and then I forgot to change something on the next step. So twice 4, 8. Now, if you stop here, I'm not going to take points off really because, so that means everybody's going to stop here. So I understand. I can't blame you. But you got to be ready for me because this is definitely, in fact, I pretty much just guaranteed that I'm going to ask you to find where this thing is flat, which is basically what you just said. So if I did ask you where does this thing have a horizontal tangent line, which is the same thing as saying where does this thing, not really where does this thing turn, because to have a horizontal tangent line you could do like a cubic. Right in the middle it rests and then it goes, keeps going, keeps going up. So here, to factor this thing, I should not have done what I just did. What did I just do that for? 4 times 15x squared plus. I can take a 4 out, and 1 4x plus 7, and 3 of those. And this is the kind of problem that my Math 178, which is what we call baby calculus, which is calculus without any of the underpinnings of mathematics, really just jump right into derivatives without describing why they work. This is what would kill them. They would not know how to factor this at all, right? Because they come right out of Math 110, which I guess is not enough factor practice. So here in the first piece, what are we going to left with?
5x cubed plus 6x.
Times 2. So that's what I had 10x cubed plus 12x there, and then I changed it back, but it should have been, because I should have a 2 times one of these. Is that cool? All right, good. So that there on the practice test answer key says 5 and 6, but it should be 10 and 12. I just lost the factor of 2. Plus, what's going to leave me left over here? It's going to be, that 4 is gone. That is still here. And what else is still there?
That 4 is still there.
The 4 is gone.
No, the 4x plus.
Oh, this one of those is still here. Good. I think at that point on the thing I just said, because I got tired. Plus I was wrong, so. But to finish this out, really, I can already see a couple places where it's got a flat thing. And really, just one more thing I got to do here is 2 more. To finish this out and to factor this. Who could factor this correctly? How many x's come out of that?
Oh, so
1, and how many of those do you have? Good. So you have an x cubed come out. Right? For each one of these, an x comes out. You have 3 of them, so x comes out, x cubed. Right? If I had 1 of these, I'd put 1x. If I had 2 of these, I'd have an x for each one, x squared. I have 3 of them, so I have x cubed. And then inside here, you end up with, what would this be? 60x cubed plus 24, let's see, plus, where am I at? 105 x squared, 24x plus 42, is that cool? And I combine like terms, I get 70x cubed plus 105x squared plus 36x plus 42. Yes, ma'am.
Okay, when you have a formula, that cubed formula, is it 5x cubed plus 6 or squared?
It's squared.
Here?
Right, above it. Yeah, it's
It's
supposed
a
to be cubed,
cube,
right?
yeah, it's a 3, yeah.
So then,
how did you take out?
then it's 5x cubed plus 6, right? At the
No.
bottom.
So, if I have 5x cubed plus 6x, go with me now.
Okay.
That would equal, how do you factor that?
You take out. Yeah, you take out x and you get 5. X squared plus 6.
So if I had 3 of these, I can take 3 and 3. Okay. End of that. And so this thing I probably have to,
Shouldn't you get rid of
I could be evil and say do synthetic division on that and see if you can factor that, but it probably does not factor anywhere near nice.
Shouldn't you get rid of that 3 then? Up top?
I can't. There's still 3 of them. I didn't divide anything away. I just took 3 x's out and I left 3 of what's left there. Yeah. But I can see, of course, where's it flat? That's where I set f prime equal to 0, so it's got a flat tangent line at x equal to -7/4, 0. This would be complex. This one I could maybe graph on the calculator and see if it hits the. This is where you got to be careful, because if you graph this in your calculator, you're looking to see where it is 0, right? Not where it's flat. This is the derivative of the function that I want to be flat. So if I looked at this in the graphing calculator, I'd see where this equals 0, find its roots. Right? Then I would add those here. It could only have negative roots because they're all positive coefficients. Does that make sense? Okay. You guys semi with me? I mean, that's why on this problem we normally do factor on this step, because normally the next step would be where's it 0?
How do you get the negative sign, Morse?
Oh, if I want to set this thing equal to 0, what would make this 0?
What would make that function 0?
Yep, that's P0. Subtract the 7, divide by 4.
Okay.
Cool. So you should be able to just look at the pieces parts and get it. If they're all
Oh, each
factored.
individual piece.
Yeah, this piece gives me this piece gives me this piece only gives me complex answers. We're not going to go there. That piece I'd have to do in the graphing calculator.
Is it because the cube, that's how it gives you complex? What gives you...
No. It's because I can't factor that over the real numbers.
Okay.
This is a sum of squares, right? 6 is squares, square root of 6 squared. So that's the sum of squares. I can't factor that over real numbers. I can only do it over complexes. It's like x squared plus 1. That would only have complex answers if you set it equal to 0. Does that